I'm back. This is about finding an algorithm's bounds on time complexity. We refer to the best case of an algorithm as omega, or big omega, or omega of f of n. The worst case is called O, or big O, or O of f of n. Runtimes can be many different functions. What really matters is the type of function that you have. You can't do better than log n, although you can always do worse. You know that no matter how bad of a job you do, you can always do worse. That was more comforting in my head. We assume that we are starting at some point where this becomes true from then on. F of n will always be between c1 of g of n and c2 g of n, and we will be using whatever constant c1 and c2 will make it work. This may seem insignificant, but it actually is quite useful. This means that f of n and g of n grow at the same rate. This works for big O and big omega too. This shows that the runtime g of n will always be between the upper bound O and the lower bound omega. Say we want to go about proving this, because proofs are fun. First, we will make up an example and assume it works. We need to find a c1, c2, and n sub 0 that satisfy this relationship. Don't you love it when relationships are satisfying? As n goes to infinity, this section approaches a half. This means that if we set c2 equal to a half, it will satisfy it. We can find that n sub 0 must be at least 6 for f of n to be bigger than or equal to 0. There are other correct answers. This is just the biggest n1 and smallest n2. For this function, we want to find the O of g of n. That means finding a c and n sub 0 that are greater than or equal to f of n. Since it is big O, you can make c and n sub 0 very large, and that would technically work. But it's far more satisfying to get a tight bound. Notice that as n grows, this will go to 0. If we chose c to be 2, then the c sub n will grow twice as fast as the n on the left. That way, even with the negative 6 on the right side will grow significantly faster than the left, which will keep the true. If n starts at 9 and only goes up, this will always satisfy. However, you could go wild and make n sub 0 any huge number you want. This shows the runtimes of different sorting algorithms. Don't worry about not knowing all these algorithms yet. We will go over them next.